In this video, we'll get another expression for the entropy of a system in terms of the probabilities of each one of the individual states. And that's generally attributed to Gibbs, although I think Boltzmann had arrived at the same relationship in a number of different ways as well. Here, just to recall, these capital P's we're using for the probability of the ith state occurring. Probability of a particle, I guess, being in the ith state. And we found the expression earlier for the Boltzmann entropy relationship in the previous video, and that was that the entropy was equal to kb times the natural log of the thermodynamic probabilities, which we'll assume that we've got indistinguishable particles, and that's the expression that we've been using for that. And Gibbs said, well, let's take a look at that and really manipulate it. So I'll substitute that expression in for the number of states, accessible states, and that's simply this expression. Again, using property of logarithms, that reduces pretty rapidly, as we've seen earlier. And then we can use the Stirling approximation, assuming all of these n's are very, very large numbers, have a huge number of particles, Avogadro's type number of particles in our system. And they're really approximations, but they're so good when we get to these large numbers that we'll write them as equalities for the most part. And we'll just substitute in to the expression up here. Natural log of n factorial is n natural log minus n using the Stirling approximation. And likewise, natural log of the n sub I factorials is this n sub I natural log n sub I minus n sub I. That can be manipulated a little bit. The sum of these two factors gives us minus the sum of the first one, minus a minus is a plus sum. And pretty obviously, the total number of particles in is the sum over all the n sub i's. That was one of our constraints. Plug that in for here, and you get a plus n here and a minus n here, which will cancel. And we're down to equation 3. And then we just have to recall the Boltzmann distribution. And the probability of the particles in the ith state, particle being in the ith state, is the number in the ith state divided by the total number, and of course that's equal to this Boltzmann factor here. I'm only going to use this front part here, and that's this, that the probability is the probability of a particle being in the ith state is the number in the ith state divided by the total number, and rearrange that for n sub I. That's just the total number times the probability. And now then we can plug that back in up here in equation 3. And when we do that, it can be written in this form. Again, we do some manipulation with the logs. The log of a product is the sum of the individual logs, so just use that relationship here. Collect terms. The n and log n, they can come outside. We have the summation over the pi's. And likewise here, the n can come outside, but the pi and the natural log pi have to stay inside the summation. But remember, probabilities summed over all the possible states have to sum to 1. And so we can substitute 1 for this term here. And that means the first and second terms are identical except for the minus sign, and so they cancel. And then we get essentially the Gibbs entropy relation. This would be for a system of n particles. You might also see it as in terms of the number of moles, little n number of moles times the ideal gas constant. But usually when people use it, they're looking at the average, essentially the average entropy per particle, and simply dividing both sides up here by n, we get the Gibbs expression. The average entropy per particle And that's sort of the traditional way of writing the Gibbs entropy expression. And really follows almost immediately from the Boltzmann entropy expression, except it puts the emphasis on the probability that a state is occupied, the state I is occupied. A couple of things I to note on this. I'm not going to hold anybody responsible for this. I really just threw this in as kind of an extra because there are traditionally three ways that people start statistical mechanics. One was looking at the thermodynamic probability, the number of accessible states, omega, or the natural log of it. Some people like to start with the Boltzmann entropy expression, and then I've seen other books and authors will start with the Gibbs entropy expression and focus more on the probabilities. It kind of doesn't matter a great deal which of these that you start with. So don't be surprised if you get a paper or you're reading some other book, and I've noticed this one has come under more the Gibbs method. Gibbs entropy expression it seems to be a little more popularity and use today, and you'll may see lectures online that other people give, or textbooks, or maybe research papers in which they'll start with that. So that's just sort of a heads up and the reason for this lecture.